Okay. This is joint work with Samira Samadhi and Tao Tantepong Puyat, who are both students at Georgia Tech, and the rest are my colleagues. So I guess most of the talk will be defining a problem, and then one part of it will have a clean solution, so I'll present that, and then there's a bunch of open problems. Okay, so dimensional reduction, we're very familiar with this. High dimensions, and there's a small relevant subspace for whatever reason you want to find it, and it leads to a nice representation with many benefits. Okay, and then maybe the most, the leading technique here is principal component analysis, where you want to reduce to some d dimensions. Sorry about the notation, but we're going from n dimensions to d dimensions because we have matrices that are m by n. I know this goes back and forth. And then one possible goal, common goal, is to minimize the reconstruction error, so the Frobenius norm of the difference between what you have and what you end up with. And you can solve this by SVD. Just go to the top singular vectors of the given data. Okay, great. Now, which also is because of the particular norm, also equivalent to maximizing the projection onto this subspace. Now, just to remind you, you could, no reason you would want to, you could write this as a semi-definite program, right? Where you want to, say, minimize the overall norm minus this projection, which is the error, right? Because of the orthogonality of these decompositions. And then x will constrain to be in two ways. First, since I want a d-dimensional approximation, I will say the trace is at most d. And then it's a semi-definite matrix with eigenvalues between 0 and 1, right? Because it's ultimately we want x to be a projection matrix of rank d, so eigenvalues 0 and 1 and exactly d once. And this is looks like a relaxation. The trace is at most d, and the eigenvalues are 0 and 1. But actually, it's exact. It's not a relaxation. Every extreme point is the SVD, because if you ended up with anything else that had rank rank higher, so the trace was less than or equal to d, but one of the eigenvalues was split up, you can always express it as a combination of two things which give you the same point, so it's not an extreme solution. So in fact, all extreme solutions of this will be rank d in this case. And there's no reason you would solve the STP. You could do it by much faster methods. Okay. Okay. Now, here is the motivating issue. You're doing PCA on this gigantic data set, but the data really belongs to two different groups, right? So maybe images of men and women. And now you're trying to find a representation in which to view these images for whatever purpose. And then the PCA, of course, ensures that the overall error is small, but the errors for the two different groups could be quite different, right? So, for example, these are experiments in the first paper here with the co-authors. This is on this data set called labeled faces in the wild. It's a huge data set that's used for image classification as a benchmark. And so if you look at the PCA on this, as you increase the PCA dimension, the error for males and females is consistently different, with the females having consistently higher error for whatever PCA subspace dimension you choose. And in fact, you might think, okay, maybe that's because there's more male images labeled in the data set. So if you normalize for that, so that you reweight data so that the total weight of the two subsets is equal, you still get this effect. Okay, and then you can see many data sets, it does happen. We have examples with credit scores and education levels and so on. So, and this is the two groups. You might have multiple groups, say, with different income levels, and you're trying to do something else. Okay, so it seems like a relevant problem. And so mathematically, it's just there are subgroups that each have their own objective, and then you get to choose only one dimensionality reduction solution. Okay, so here is the problem. You have these data matrices, AI, k of them, and a projection matrix is what you want to pick. And if you gave me a projection matrix, then the error of every data set, let's say in this case, would be this Frobenius norm of the difference of the error, which you can rewrite like this. And you have a target dimension d, and your problem is to find a single projection which of rank at most d that minimizes the maximum error of these groups. So that's.
I have a question about your error. So trace is a scalar, and A transpose AP is a matrix?
No, by that dot I mean the inner product there. So this matrix inner product with the projection. I just expanded the Frobenius norm here. And so we're left with
It's a
this
drama.
matrix. Sorry? Yeah. So one possible objective here might be to minimize the maximum error. But you could also do lots of other things. For example, maybe it's not the maximum error that matters. Maybe it's the maximum marginal error. So you know, if you were to find the optimum for subgroup A and for subgroup B, you get some optimum. And then you want to find a common solution. By switching to the common solution, subgroup A pays a certain cost, subgroup B pays a certain cost. Maybe you want to minimize the maximum of those marginal errors. You could have a number of different functions. We'll see a couple of examples. Another one is the Nash social welfare, where you maximize the product of the objectives rather than the, and this is actually what's used in the bargaining problem. So here is the fair PCA problem. You want to minimize the maximum error, whatever error is defined as, over these different groups, where you're picking a projection matrix so that its square is itself, and its rank is D, and it's symmetric. That's the goal. Yes?
So why not have for each group a different model? And why not the whole board?
Because I want to pick one D-dimensional subspace. At the end of the day, I want to pick one dimensional subspace. That's where I'm going to run my algorithms, whether it's nearest neighbor or clustering or what have you. That's where I'm going to run the algorithms.
So would it not be practical maybe to first detect whether male or female and then run whatever?
Run a separate one? I mean, sure, that's a possibility. But I mean, sometimes the goal of the algorithm is to detect whether the image is male or female, or to label the image, or and so on, right? So I mean, I don't want to burden or constrain the problem. Yeah. The application. So this is the fair PCA problem here. Yes.
PCA is unsupervised learning, but if you know the group labels, then why don't you supervise learning like LDA?
To do what? With what goal?
Dimensionality reduction, I don't know, for some purpose. Because you already know the group labels.
I know the group labels, yes.
So if you know the group labels, then PCA is not a good method for dimensionality reduction. There are more effective ones like LDA.
Which assumes certain model and a certain problem, yeah. Sure. But let's say my problem is to choose a subspace. Here's the definition of the problem. LDA would make no sense here in the worst case, right? It would maybe if you assume a distribution on the rows of the two groups, possibly it might work, but even that is not clear. Yeah. So now just keep in mind that, like we did for the case of a single group, we can write down a semi-different program still, right? So you want, or at least a rank constrained one, where you want to minimize the maximum error. That variable is just bounding the error of every group, and you're minimizing the maximum. The rank is D, and your projection matrix is between, it has eigenvalues. Yes.
So this is sort of assuming that the fair thing to do is to correct some, or correct some kind of dimension reduction, but you're going to use the projection into the principal components to take some action, presumably. So wouldn't you want to say, I want the action to be fair?
Oh, right. So, but I don't know what the action is going to be. I do know that this representation will be used as a basis for some algorithm downstream, whatever that might be.
Okay.
In fact, that's how it's commonly used, right? It's just PCA itself is a pre-processing step to later things. Yeah. And you might contest, though, why maximum? Maybe that doesn't make sense, or why this particular objective? Just like that's certainly a valid question. For the moment, I'm saying if you keep it as maximum of some error of each subgroup, then you can still think of it as a semi-different program, where now we might imagine replacing the rank constraint here with a trace constraint. Okay. So now, how about more generally? So sort of getting at that, but not. We still want a d-dimensional projection. So we have some function, utility function, that measures the utility of each group. Each group might have its own. Maybe it's not squared error. One group cares about maximum error. One group cares about some other norm, so on. And then and then on top of that, there's a function over the k utilities, the k groups. So there's a function over the k utilities. In our case, it was min, right? It was the min function, minimize the maximum error. But it could have been something else like the product or whatever function. And this is the general problem. You have these multi-criteria and an objective on top of those, and you want to find a single projection that works. So again, the case of minimizing the loss, you can think of as this is the optimum for each group, the optimum error. This is what you would get if you use the common projection P, and this is the loss for the ith group. You want to minimize the maximum of these losses. Okay. Now, actually, if you looked at this loss, this is what happens. This is the loss for females, the loss for males. If you did standard, you're stuck with the PCA. Whereas if you do fair PCA, you end up, which I'll show you, which I haven't shown you yet, the algorithm for it. You'll get something in here, which at least in this picture seems more fair or more balanced.
Fair male or the fair female?
The green one is for both. They get the same loss, and that's a theorem. For two objectives, you'll always get the same loss.
Oh, you don't.
Yeah. Okay. So again, you can do this. So this you have these general functions, and here's a second example I was mentioning. Instead of min, you could use product, just a second well-known function that is used. Okay. There's a bunch of related work on rank-constrained semi-definite programs. They come up in signal processing, even in machine learning. There's a survey by Davenport and Romberg about the use in signal processing. And as we'll see soon, the approach we'll take is related to some classical results about semi-definite programs by Barvinok and Pataki. And an even earlier result called the S lemma, which lets us verify whether a family of quadratic inequalities is true. So we'll come up with that. So here's the first theorem, that the fair PCA problem is polynomial time solvable for two groups, exactly. Okay. So this was the fair PCA problem, and it's polynomial solvable. And it generalizes to fair dimensionality reduction as long as each utility function is linear and the overall function is concave. As you can imagine, this is sort of preserving the convexity of the whole thing. But so this fair dimensionality reduction problem, as long as each of these is linear, which it is for the PCA problem once you write it as AA transpose and a single matrix X, and the overall function is concave, the problem remains polynomial solvable for k equal to 2.
Excuse me,
Yes.
could you explain what you mean by polynomial time solvable? Because the SVD, you cannot do it in finite amount of time to compute an SVD, right?
Well, you can do it in polynomial dimensions and log 1 over epsilon.
No, if Galois theory tells you, you cannot compute the roots of a polynomial of degree.
Oh, sure. By polynomial time solvable, I mean for any given accuracy epsilon,
I see. So
the dependence
you
is
have an epsilon.
it's logarithmic in 1 over epsilon. And that's also true for semi-definite programming. Yeah.
And so in what is the epsilon?
The user can pick, because the dependence is logarithmic in 1 over epsilon.
So one as a function of p, the use could be convex or concave, whatever.
Linear only for this.
Only linear.
Linear.
You don't allow.
No.
You can't do other things.
No, can't do other things. At least not with this approach. And I don't know if it's hard. It would have to be convex, I guess. But yeah.
I mean, you're just going to write inequalities. Let's say.
Just going to write inequalities, but I
But
made.
if they're convex, that still should work, right? No.
Yeah.
The inequalities will still be a convex set.
Yeah. The problem is that we will need inequalities that relate two of them. Yeah.
I see.
So linear is okay because it keeps the convexity of the whole solution.
But you're minimizing the maximum, so you just say that's all like greater than or equal, less than or equal to something.
Less than equal. Let's say u is quadratic.
Oh, I see. But that one thing, yeah, okay.
Okay, so that's the setup. Now, this was the, sorry, I stated the result for two groups. This is actually a special case of the main result, which is that for any number of k groups, there is a polynomial time algorithm which will give you a solution whose cost is at most the optimum cost for k groups, but the rank will be violated by square root of k approximately. Right, so instead of rank d, you'll get rank d plus square root k. Okay, rank d times k is trivial. You just take the d, the k different best possible maps for each one. Take the union. So this is d plus square root k. And this already implies two groups is solved exactly because this number is less than 1 when k is 1, and when k is 2. And then this also generalizes to fair dimensionality reduction under this concavity, u is linear, g is concave condition. So this is sort of the main algorithmic theorem here. Now, if you care about keeping exactly d, you don't want to make the dimension more than d, then you can turn this into the same algorithm by just asking for a smaller dimension up front you can make it a 1 minus order square root k over d approximation to this maximization problem. And then there's no rank violation. So you can get either of the two. It's criteria as an approximation.
And the different groups have different objective values if k is greater than 2, potentially?
Yeah, the use can be anything you want as long as they're linear. Yeah. Okay. Then, in fact, using a classical theory of quadratic maps, this fair dimensional reduction problem is polynomial time solvable for constant k and d. So if k and d are constant, then it's polynomial solvable. This is the and then the functions don't have to be linear. They can be any the ui's can really be any function, and the g, all it has to be is approximable by a polynomial in a subring, which lets you do all of these things, like you can do min plus and all that. And now you can of course ask, is there a hardness here? Why aren't we doing this for everything in polynomial time? It is hard when k is part of the input, even for one dimension. So if you want the best one-dimensional projection for an input k number of groups, it's NP hard by reduction from max cut. I don't know the approximation hardness, but so that's the layout. Now, sorry, yeah. So here is the sort of maybe the main structural theorem that, since we're bridging between discrete and continuous, yeah.
Sorry, so for the previous side, the hardness was when the U's were, the hardness is when the U's are something general?
No, even for the fair PCA problem. Just minimize the L2 error.
Oh.
The Frobenius norm error when you're projecting to one dimension. So think of top principal component
I see.
with k groups.
Okay,
Yeah, that's hard. That's NP hard.
I see.
If you want to find one component that simultaneously minimizes the maximum error of all k groups, it's NP hard. Okay, so here is the sort of main theorem here. That if you have this rank constraint SDP here, and this is just a single linear constraint on the semi-definite matrix. So yeah, I have one linear constraint, rank, and the eigenvalues constraint between 0 and 1. Okay, and then I'm minimizing some linear objective. If I replace the rank with a trace constraint, then the optimum remains the same. So you get for free the rank D even if you go to trace. That's the sort of main side. I'll prove this completely. And so as a result, fair PCA is polynomial time solvable for two groups, because the constraint I will just say is one group is less than the other group, and then minimize one of the groups. So with two groups you only have one constraint and one objective, and so it will be polynomial solvable for two groups. Okay, this result generalizes this classical result of Pataki and Barvinok, where they showed that without this rank constraint, they had inequalities over semi-definite programs where you didn't have the not rank constraint, the eigenvalue constraint, the upper bound on the eigenvalues. Okay, so if you have any number of inequalities and you don't have this part of it, so semi-definite program with set say k inequalities, what is the maximum rank of extreme point solutions? And they bound it by roughly square root k. That's the result. But here we need to extend those because we have the rank and the upper bound on the eigenvalue constraints. They go together. So that's the main.
For a non-convex region, right? The upper bound.
Sorry.
The upper bound makes it non-convex program. If you're only lower bound, it will be convex because.
I mean, over here, this SDP is just an SDP. So this is still convex.
But the maximum. Oh, I see. Okay.
This is still because this is just eigenvalue condition. So this is x is the only variable. So this is still convex. There, of course, it's not convex. Yeah. Okay. So the general version of this, where these two are identical, is that when you have m constraints, then it goes from the rank can be violated. The extreme point solutions of this don't have to be rank D, but they will be rank at most D plus square root of the number of inequalities, basically, which is less than 1 in the case of one constraint. Okay, so that's how you get the main theorem. Okay, so let's go to the main theorem here and do it for just two groups, which is one constraint and one objective. Okay, how does this work? The main claim is so that there's the SDP, right? The trace is smaller, you have m groups or whatever. And now let's just think of 2 groups. So 1 constraint. And let's take an extreme point. The only claim is that the extreme point has rank D. That's it. That's all I want to prove. An extreme point has rank D in this case, even though you have a constraint and an object. So let it be an extreme point, and let's say suppose it has some R fractional eigenvalues. So eigenvalues that are not strict, that are not exactly 0 or 1. We've already guaranteed that all eigenvalues are between 0 and 1. So here are the eigenvectors for eigenvalue 1, eigenvectors for eigenvalue 0. It might be multiple choices, just pick one basis here. And then these are the eigenvectors for fractional eigenvalues. That's how I've decomposed x. I should write x equal to this. And then here are the eigenvalues. Once, this is some diagonal matrix of fractions between 0 and 1, and the rest of it. So we've got this matrix here. Now, yeah, I'm just stating that in words. Now here is the main claim. If the rank of this, the R, the size of this diagonal matrix is such that R times R plus 1 over 2 is bigger than m plus 1, so R is a little bit bigger than square root, or a little bit small, about square root 2m, then there exists an R by R symmetric matrix F, so that I can add F to D and I can subtract F from D, okay? And these remain feasible for the SDP. So basically proving that it's not an extreme point, right? Because I've got an extreme point solution, I'm perturbing it this way, perturbing it that way, so that this original point is still the average, and both those are not are feasible. So it's clearly not an extreme point. Okay, so I have to prove the claim, but assuming the claim, it's clear that it's not an extreme point, and therefore the condition you get is that R times R plus 1 over 2 must be less than or equal to m plus 1, and then you're done. Now I mean it's the eigenvalues of y and z will be the eigenvalues will be the eigenvalues of these diagonal parts of the matrix, because this is just an orthogonal. The left and right matrices are orthogonal matrices. Okay, so we just have to prove the claim. Might be too far. Okay, so this is the claim. I'm restating it again. I guess it wants me to go slowly. Yeah. So we want to show that there is a symmetric matrix which keeps feasibility even if you add and subtract it. Okay, so we'll do this by elementary linear systems. I want to find such a matrix F. Oops. I guess my excuse me. Let it stay. Okay, so I want to show this is true. So consider the following linear system. Right, we want to find such a matrix F, show that it exists. And the way we'll show it is just that there's a linear system with more variables than inequalities, and therefore, or at least as many variables as inequalities, and therefore there's a solution. That's it. So why is that? What do we want this matrix G, that's the variable, to do? It has to be, well, I want to keep it orthogonal to these, to that subspace of fractional eigenvalues, stay in that subspace. I want it to have trace 0, so that it doesn't violate the trace condition, in fact stays whatever trace it was, and I want it to be symmetric. Okay, so if I can find such a matrix, great. Now there will be such a matrix. Why? Because the number of equations here is m plus 1 plus, for the symmetry, r times r minus 1 over 2. The number of variables is r squared. Yeah, it's r squared. It's symmetric, but I put in the conditions explicitly, so it's r squared, right? So now if r squared is bigger than this, then there is a line. I want actually strictly bigger, so that there's a line of solutions. There's a one-dimensional subspace of solutions, and it's not 0. So that this whole line lambda g is a solution. And now what we can do is we can pick an epsilon small enough and make f to be epsilon times g. The reason I want to pick epsilon small enough is that so that even when I perturb, the eigenvalue stays between 0 and 1. This had eigenvalues strictly between 0 and 1. There must be an epsilon I can add so that it stays between 0 and 1. That's it. Add or subtract doesn't matter because it's strictly between 0 and 1. That's the proof. And then if you go to these m, we get that it has rank at most d plus square root m. Actually, we proved the general theorem. And you can do this with affine constraints and so on. Last thing I wanted to mention is that one of the nice things in combinatorial optimization is iterative rounding for various problems. Yes, sorry.
When you talk about
extreme points beforehand, do you just mean anything that's sort of on the boundary, the feasible set?
Oh,
or anything that's
extreme point solutions of a convex set, meaning that the point cannot be expressed as a convex combination of any other feasible points.
Okay, so this means you have to use an algorithm that guarantees you don't just have an optimal point, but that you also return express.
Yes, which is actually quite a well-studied thing in convex optimization, because it has many benefits besides this. So basically, if you are at such a point which is optimum but not necessarily extremal, you project to that subspace and continue optimizing that subspace till while you keep lowering your dimension till you get stuck to at a zero-dimensional space. Yeah. So yeah, indeed, you can do that. So iterative rounding is this process where you have a discrete problem, you relax it with a convex relaxation, you have a fraction solution, and then instead of trying to round the fraction solution all at once, you realize that some one variable or some small subset of variables can be made 0 or 1 quickly without losing much in the objective or the constraints, and then you repeat this whole process. This was very successful, for example, for finding spanning trees with degree constraints on them. This was actually by my co-author Mohit Singh, and earlier for these general Steiner forests and so on. But in SDPs, this was not there. So here you can turn this insight about extreme points into an iterative rounding algorithm, which basically maintains a subspace of 0 eigenvalues and 1 eigenvalues, and shows that from the remaining subspace you can either drop a constraint or move one of these to a 0 or 1 eigenvalue, and thereby make progress. At the end of the day, this gives a guarantee that instead of violating the rank, you get a violation in the objective value. But this violation is sort of a funny thing. It's this quantity. We can go into it, but yeah, it doesn't give a worst case improvement over what I've already stated, but it sounds like there should be something interesting down this line for maybe this problem or other problems by using rounding. Now experiments. So this thing is so if you do STP relaxation, it actually does quite well and performs optimally a lot of the time. But with SDPs you can't go very high. These are just MATLAB experiments. On the other hand, we can solve this class of SDPs with the multiplicative weights method, and then we can go up to 1,500 size data sets in minutes, and then in the multiplicative weights method here, the core subroutine becomes PCA, because all you have to do is find a weighting that's the worst one. So instead of one PCA, you end up doing a dozen PCAs, and that's the price of fairness. Okay, for 2 groups at least. The code is publicly available. You're welcome to try it out at Samira's webpage. So here's a fair dimensionality reduction problem. Maybe there are more objectives, nicer ones. One thing I haven't yet proposed at all is the use of sketching methods, which have been great for multi-criteria optimization in other contexts. Maybe it makes sense of fairness too. What's a fair sketch even is a question. This notion of low rank solutions under constraints on the eigenvalues seems interesting. There's iterative rounding. Maybe there are other applications, potentially to discrepancy theory. This is what I'm thinking about. And yeah, thank you.
Rounding, right? If you had a linear function, the g was linear, and you give me one more rank, then every extreme point has to be, every optimal solution has to be an extreme point, isn't it? Because your wiggle.
Yes, right.
So one more rank.
Right.
Yeah.
Right. Yeah. Yes.
If you just take your problem and define it for linear regression.
I'm sorry. Linear
If you
regression.
just took the exact same problem is that an obvious solution? Is there an obvious solution to that?
Yeah. This works that fits in the framework.
But that wasn't known before your work, basically.
I don't think so. For 2 groups, once you go to 2 groups, you have to do something non-trivial. You can't just use PCA. It would have been nice if you could say run a single PCA on this somehow created matrix.
Yeah, right.
I struggled there. I couldn't get that too. That would be nice. Yeah, but
You cannot do anything like put all the AIs in.
Yeah.
You probably tried all those.
that is the whole data set, right?
Yeah.
So that would be the single PCA.
But
That doesn't work. Yeah, weighting also didn't say, yeah.
In your multiplicative weights, when you know like it's going to be a learning solution, can those be partial PCAs, or those are all the full data set SVDs? Like,
Oh,
they
at
just-
the
you
moment,
just-
at the moment we just do full data set SVDs. But I can imagine that you should be able to save on the iterations as you go along. Keep the previous one and then use that as your starting point for the next.
Right, or maybe like only compute the top, like some to the top, to all the eigenvalues.
Right. Especially because you're just using it as a certificate of non-optimality. Yeah, maybe you do an incremental PCA. The point where you find the violation, you use that, and yeah, no, I haven't. Right now, it's just run
But it could be very
yeah. At the moment, I mean, with these naive sort of implementations in MATLAB, it's letting you go to 1500, and those experiments that I showed you on those real data sets are all, we ran them. No professional advice. So. Yeah.
You say when, so the iterative rounding algorithm doesn't give improvements in the worst case, then you say when.
I mean, you can come up with cases, but worst case, we don't have a bound that actually is better. Yeah.
When is it like very good, for example, much better?
It's very good if the eigenvalues of the groups are sort of they don't decay to. I mean, they have a nice spread among the top D that you care about. Then the averaging that it's doing is really good. Yeah. Yes.
So does this ensure like the variation between any two classes is maximized so that these classes are more and more separable?
I guess it ensures that the D dimensions that you're choosing, that the subspace you're choosing has maximum variance. I mean, that's the general PCA objective. It's not a clustering problem that I'm solving, right? If you solve clustering on top of this, let's say you did k-means plus PCA, then you could ask, what's the final guarantee? And I don't know. I mean, it would be.
I think somebody asked you like the discriminant analysis actually guarantees that. So.
Well, that's under a certain generative model, not worst case data.
So it's a generalized eigen problem. So
Right.
it's like it maximizes the variation within classes and minimize the variation. So maximize the variation between classes and minimize the variation within each class.
Right.
And it kind of maximize the ratio of these two.
Yeah. Yeah, for that objective, yeah.